Hi, everybody. I am Brian Brinker,
And my name is Osayuamen Imaswin.
and we are both online electrical engineering students. And this is our presentation for our EE 457 Intro to Robotics. Note that since we are both online students and there's quite a bit of distance between us, we decided that since I'm the only one with the 3D printer, that it would be smarter to purchase a robot so we had the exact same physical model in front of us so we could each experiment and problem shoot with it. So as we get into it, here are some of the topics that we are going to cover. So once I received my physical model, the very first thing that I started doing was doing a virtual model in Fusion 360. As you can see here, let me get my videos playing. Um, First thing I did was draw the model of my robotic arm. Each link is the exact same, and the degree of freedom in each link is also the same as my actual model or as my actual robot. Obviously, the colors are offset, and that's just for visual effects, so you guys can see the difference in the links.
This section shows how we mathematically model the robot. We use the Devinant-Hattenberg's parameters to represent each joint. We have theta, which is the joint angle. We have D, which is a link offset, and we have A, which is a link length, and then we have alpha, which is the twist angle. From these parameters, we built transformation matrices that describe how each link moves relative to the base. The DH table describes the robot's geometry using 4 parameters per joint. This is the physical structure of the robot. It consists of the base joint, which is J naught, the shoulder joint, which is J1, the elbow joint, which is J2, and the wrist joint, which is J3, 4, and then inside of that, there's a gripper which performs the actual manipulation task. Each link length is measured and modeled so the robot can be simulated accurately in MATLAB. So the physical link lengths measured from the robot are D1, which is 117 millimeters, A2, which is 58 millimeters, A3, which is 62 millimeters, and A4, which is 102 millimeters. Each row defines one link transformation relative to the previous one. By multiplying 4 homogeneous transformations together, we get the final transformation in a 4x4 matrix that tells us the gripper's exact 3D position and orientation vector.
Since we were working with a pre-built um, arm, we decided to use forward kinematics to calculate and describe the end effector's position and orientation along with their angles and link lengths to the item that we were trying to pick up and move. You can see our math here, and that relates directly to the DH table that you saw in the previous
So
slide.
based on the forward kinematics tell us where the end effector is located based on the joint angles. We use our DH table to derive the transformation matrices, multiplying them. That gives us the full pose of the robot in a 3D space, which you guys will later see in the later slides. Next, we computed the Jacobian, which tells us how the joint motion translates into the gripper's motion. This matrix is essential for task-based control and inverse kinematics. The Jacobian maps each joint angular velocity to the linear and angular velocities of the end effector. The Jacobian tells us how small changes in the joint angles affect the robot's motion. It's essential for inverse kinematics, singularity analysis, and controlling the robot smoothly in the task space. We derived our Jacobian using the standard cross product method, and every term depends on the link lengths and the compound angles. Next slide, please. So here we have the symbolic Jacobian, which shows link lengths and joint angles combined. Terms like sine theta plus sine theta 2 plus theta 3 plus theta 4 appear because the joints are serially connected. This means that the motion of each link depends on all the joints before it. When I start rotating the joint even a little, the gripper travels in a certain direction. Each joint makes the gripper move differently. The Jacobian captures all of those effects in one matrix. A question you can ask is, if I wiggle the joint, how does that, how does it, how does the tip of the robot move? Um, the Jacobian is also a derivative of the DH table parameter geometry. It tells us how each motion at each joint translates to the motion of the robot's end effector. Next slide, please. So here we have the models, the physical models and the motions of how the robot is supposed to be moving in a 3D space. You have such as the task-based control using the forward kinematics, the Jacobian, and pseudo inverse to move the arm along a smooth path in 3D space. It allows the robot to reach a point even when required joints angles are not obvious. In this is the foundation of many modern robotic controllers, including computer vision tracking and manipulation.
So here is the actual robot programmed and moving the block off the simulated conveyor belt onto what we'll call a loading station. As we are watching the video, I'd like to go over a couple issues that we had when building the system and things that we had to overcome. Number one is programming the robot. So at the time of trying to code, I did not realize that the pinout locations for an ESP32 and an ESP32-S3 are slightly different. On the S3, there are very specific pins that have to be used for servo motors. Those pins are 5, 7, 9, 10, 11, and 13. Any other pin will make the robot go very sporadic. Also, a couple other issues that we had is during that sporadic movement that I was experiencing, I did burn up the original motor, which is an LFD-01M. Luckily, I had a replacement MG90S. The only difference was the torque specs for the motor replacement, which obviously did not affect it for our use. A couple other things is that it was very particular to wire length coming off the servo to the board. If the wire length got too long, the voltage drop was too much and the servos would not work. Also, I was experiencing a tremendous amount of voltage drop when all the servos would activate at one time. So I had to do calculations in order to make sure I had enough capacitance in order to run the system. All of these things will be presented in our final paper as personal recommendations of things to look for when trying to purchase or design a robot, and that will be found in the appendix of our paper.
Thank you.